Hello, so my final project is on autoencoders and variational encoders. And for the problem here, I investigated the differences in the outputs, the architectural differences in the implementations, the loss differences, so the sampling differences, and some use cases we can use these two different architectures. So we can first start out with explaining what autoencoders do and what they are. Basically, an autoencoder just passes through each pixel using convolution or just passing through pixels into each layer. It has an encoding function, this part, and its encoding function past the bottleneck here. The main use cases for autoencoders are to discard noise or pixels as based on the training data that the neural network is trained on. For the encoders and decoders, they're basically the same. There's no difference between them, so we can go back and this part would be same thing as that, but they pass different shapes and variables. So the encoders are multi-layer perceptrons, and they convert, or at least the decoders convert or encoders convert the image to latent and hidden variables, and the important parts are compressed into the latent variables. And the number of parameters, latent parameters used depends on what or how much you want to keep of the original image. So the larger number means more of the image is kept. So we can talk about the latent space, which is the bottleneck here of the in between the encoders and decoders. The latent space is important because it basically reduces the dimensions of, or is the result of the dimension reduction of each layer after the encoder, and the decoder decodes the latent space variables. So each layer, if we add more layers, then we're able to have more separation of, I guess, the uniqueness of the image here. So the more layers, the more the variables are able to be affected by the other ones, and the weights are changed by each layer. For the training here, to get the loss here, it's just the difference between the input and the reconstructed image after the decoding. It uses gradient loss, or at least how I did it. It is unsupervised learning since it doesn't need labels to learn the general structure. As I said, the encoder reduces the dimensions, and I said the layer separates the features of the image or data set. And its decoder rebuilds the dimensions. And for some use cases here, it's not limited to images, so you can use it on words using tokens. You can use it on image recognition since it's able to generalize the important features of the images. Noise reduction since if you wanted to remove I guess the uniqueness, not the uniqueness, but the noise, I guess that's easiest to say. It generalizes the data, so it takes the general data of image, and it's able to recognize patterns in a data set since it's training multiple images. And some problems with the standard autoencoder are that this also applies to the variational encoder's compression, since it reduces the image size, so depending on the latent space size, it reduces it by that much. And also, if the latent space is too large instead of too small here, the neural network can just be the identity function, which is just whatever image you pass in, it just spits out the same output image, so it encodes and decodes the same image, so with zero loss or close to zero. And for the standard autoencoder, it's gonna directly encode the image instead of with the discrete variables, or not discrete, but discrete outputs. So there's no variation in the possible, I guess, latent space variable. So now we can talk about the variational encoder architecture. It's pretty similar to the auto encoder, except for the latent space is the only difference. Instead of discrete values used, it instead uses a continuous probabilities of values. And compared to the simple autoencoder, the variational encoder can generate different outputs since it has probabilities. It uses probabilities of the latent variables. It uses Gaussian samples to get those variables. I mean, get those continuous variables. And any random variable can output a meaningful um, image or data here. It gets the continuous distributions from calculating the means instead and the variance. So using these two, we can get the probabilities. I guess we can quickly go over the dataset and the samples I've gotten from my code. The website's here. It's just 52 images of the cards in a deck. For the first sample, the autoencoder uses 100 latent variables with 30 epochs. You can see it can pretty decently get the cards that are discrete, black and white, and just has a number of spades in the middle. However, for these ones with the black backgrounds, it's not able to get the discrete information since it pretty varies from the standard decks here. And also this one, it tries to form as the other ones, but it gets the queens properly since it's a lot of training data of the queens and kings. This one is a bit too varied, so it doesn't really get any useful information from that. This one as well, it tries to make something out of nothing. So, yep, and I guess we can go over the next one. This one has more training data, so it trained on more cards. It's a bit better on the black backgrounds, but not that much. This one as well, it tries to have more than what it has, a lot more. This one, it can't really discretely get any information from this. And for the variation one, just only 2 latent variables and only 5 epochs. It's pretty decently able to get this black backgrounds cards here. However, it's not able to get varying discrete cards here because it's only 2 variables, so they all look pretty much the same, just a bit different. That's why we should increase the latent variables. So the next one with 100 and 24 epochs, so more training. And this one's, I think it's the full data set we trained on, so it's able to get these ones and even get these shapes properly. The kings are pretty, or the jokers and kings are pretty well trained and encoded. Even the black backgrounds with queens is able to get a variation from these ones, even though it's different color. This one as well. This one not as much. Yes. And for a variance sample, which displays the variational parts better, since it's able to make a continuous difference in, I guess, this one's 2 black backgrounds to a white background. Only 2 latent variables, so it's not much to this. For the next one, it's 100, so we are able to get more information. This one you can see is a bit of a king, but this one you can see it's a black background, so it's able to get that. It's able to change into a 4 or spades of clovers, whichever one it's trying to look like. This one's opposite spectrum. This one, I get this more information in the middles for these ends here. And for just single samples here, this is an ace I created from Paint. You can create images here, but this is not great. This is just using the simple autoencoder. This one's only 2 epochs and 2 latent variables, so not that great. But for the variational one with 100 latent variables, it's able to get the same shape here. However, this one should be hearts. It's probably because the training data didn't have the right colors for hearts. It was red, so it's not able to get the black color. However, this one, it's able to get these 4 discrete ones with some information for the 4 there. And this one's a variational one, but has more training. I think it has more latent variables than the other one, so it's able to get the spades closer to clovers here. And here's the references for the websites, and that's pretty much it. So here's the demo of my network. So you can just open an image here, choose a random one, and it should display the encoded image and decoded. Test it on other images.